Hello from Lincoln, Nebraska, here in the United States. I see we have a pretty large group here today, a lot of familiar names, people we've talked to at meetings, helped with technical support. It's nice to see everyone here. Also looks like we have a worldwide crowd here. So the goal of this educational webinar series is to share information and experiences within the communities, to emphasize two-way communication and be interactive with each other, and also to help new and experienced researchers and scientists with learning new techniques and sharing their own experiences. We're going to go through 5 different Eddy Covariance webinars. We're going to go through one per month, and we'd like to encourage you to invite your coworkers, colleagues, and other people as you see interesting topics here. We're first going to cover some overview and basic theory. That's what this particular webinar is. The following webinar will cover instrumentation experimental design, talk about setting up Eddy Covariance sites. The third webinar will go into data processing, looking at software, how to compute fluxes from your raw data. Then after those 3 webinars, we're going to take a little more of an in-depth look at both the theory and experimental design, really covering all the different corrections, data processing principles, and then how to use advanced software to compute your fluxes. So we have a pretty established scientific flux team here at LI-COR, dedicated to Eddy Covariance. A lot of these webinars are constructed and will be delivered by members of this team here. You also will meet several of them through being panelists and helping to answer your questions as these webinars are broadcast. And beyond the webinars, we're always going to be here to help answer any of your Eddy Covariance questions. So now to get into the first webinar here, the theory and implementation. Again, I'm Dave Johnson and my colleague Jia-Hung Lee. And we're going to first cover why do you need the Eddy Covariance method. Jia-Hung will then talk to you a little bit about what the Eddy Covariance method is, and how do you make Eddy Covariance measurements. And I'll come back in and talk about where and what kind of applications the Eddy Covariance method can be used in. So first, I wanted to see, I feel like we have a fairly diverse audience here, level of attendees, but I wanted to put a poll question out there to find out how much people know about Eddy Covariance.
Thanks, Dave. Since this is our first poll for the webinar, let me walk everyone through how to answer the poll. The poll should be up on your screen now, so just click the radio button next to your answer and hit submit. Now let's give everyone a few moments to respond.
All right, well, thank you for participating in that poll. That really helps us become an interactive experience. As I thought, there is kind of a wide variation of knowledge between the attendees here. So now as we move on to this next slide, we're going to talk about the general definitions and make sure we're all on the same page. First, we're going to talk about flux. Flux in this particular area of research is how much gas or energy moves through a unit area per unit time between the surface and the atmosphere. And here, when we're talking about Eddy Covariance, we're going to talk about fluxes that are originated from and integrated over an area the size of ranging from hundreds of meters up to kilometers. Most of you are familiar with this particular diagram. We have the carbon cycle here, where we're going to show 4 storage terms where carbon is stored. We have the atmosphere at the top. Along the bottom, we have fossil fuels, soils, and the oceans. And the arrows represent the direction of fluxes of CO2 in and out of the ecosystems and the atmosphere. As you can see, the photosynthesis and respiration of the ecosystem contributes the largest transfer of carbon, even more than the fossil fuels and the deforestation. You can also see while the oceans are large and have a large sink of CO2, they're still slow for carbon exchange, comparing it to terrestrial ecosystems. This picture is the hydrological cycle. H2O is often the forgotten greenhouse gas. However, many feel that water is more important than CO2, especially when it comes to regarding short-term resources. Precipitation brings water into the ecosystems. You can see the red circle there showing 113. But as H2O makes its way to the different storage areas, for example, the ocean and lakes, that about 65% of it is lost up through evapotranspiration. So it's important for flux measurements to be able to measure these evapotranspiration rates. And Eddy Covariance can also be used to study different changes to the ecosystem that have an effect on evapotranspiration. So I'm going to turn things over to Jai Hung. He's going to talk about the Eddy Covariance method, what it is, and how to use it.
Thanks, Dave. While Jihong is getting into place, let me remind our audience that if they are a member of the Twitter community, they can follow the conversation about this webinar by using the tag #EC-Series. Jihong?
Thank you, Ashley. Thank you, Dave. To understand the Eddy Covariance method, we need to first look at the atmospheric boundary layer. The boundary layer is divided into several sublayers. Each sublayer has its own identity. For example, wind speed increases with height in the surface layer and becomes constant in the mixed layer. In the constant flux layer, because the flux variation with height is so small, the flux is considered constant in this layer. Let's take a closer look at the constant flux layer. Based on decades of scientific research, we can reasonably assume that gas transfer in the constant layer is conducted only by turbulence mixing, and there is no divergence and convergence for homogeneous horizontal terrain. Under these two assumptions, the fluxes at x and y direction are equal to 0. This sounds hard to understand. To better understand this, just imagine a box above the canopy. If there's 1 gram of CO2 coming into the box, and at the same time, there's 1 gram of CO2 leaving the box, the amount of CO2 inside the box doesn't change. You can easily see that if you could figure out a way to measure the flux in the vertical direction, we would be able to determine the flux of this layer. The instant vertical flux is equal to dry air density multiplied by vertical wind speed and the gas mixing ratio. In order to get the mean flux, we partition the incident variables into means and deviations based on Reynolds decomposition technique. As you see here, the O bars represent means, the prime stands for deviations. After we simplify equation 2 using Reynolds decomposition, we get equation 3. That is the final covariance formula. Flux is equal to mean dry air density multiplied by the mean covariance of vertical wind speed and the gas mixing ratio. With the general Eddy covariance formula, we can easily derive the formulas for CO2 or methane, water, and the sensible heat fluxes. In this formula, the K components are the mean covariance of vertical wind speed with CO2, methane, water, and the temperature. That's why the method we are discussing here is also called the Eddy Covariance technique. With Eddy Covariance theory, let's see how to conduct an Eddy Covariance flux measurement. Basically, we need a three-dimensional sonic anemometer and a gas analyzer. The sonic anemometer measures wind speed and temperature. The gas analyzer is used to measure CO2 density, water vapor density, or methane density. The sampling rate for both instruments needs to be at least 10 Hz, that is 10 times per second. To demonstrate why we need the high-speed instruments, let's see a quick animation. Imagine an eddy traveling along the wind direction at time 1. At this time, when the instrument takes measurements, the eddy is away from the tower. Because this tower has a 10 Hz sampling rate of 1/10 a second, when the instruments take the next measurements, the eddy will have reached the tower and be measured. For the same eddy measured with a sampling rate of 5 Hz, when the instruments take measurements at time 1, the eddy is away from the tower. However, when the instruments take next measurements up to 2/10 a second, the eddy has already passed the tower, so this eddy measurements is missed. Based on the type of gas analyzer in flux measurements, an eddy covariance system is usually classified as a closed path or open path system. In an open path system, the air moves freely through the measuring path of a gas analyzer. In contrast, in a closed path system, the air is forced into measuring paths by a pump. Here are three major differences between the open path and the closed path systems. The open path system consumes much less power because it doesn't need a pump. Under raining, snowing, or ice conditions, both systems have difficulties collecting accurate data, but the closed path system loses less data than the open path does. I'm going to stop here to let you take part in our next poll, and let David take over the talk. Thank you.
All right. Well, thanks everyone for taking part in that poll. Those are some interesting results. Talking about instruments, there's some key important aspects from using instruments in ecosystems. We know that people want to measure research all over the world in different locations and different ecosystems. We have research sites that are located up in the Arctic and all the way down in the Antarctica. We also have people using these in rainforests and the Everglades. So the instruments really have to be rugged. They have to be weatherproofed. They have to be insensitive to dirt and dust, to all the elements. They have to be able to be outside where they are rained on all the time. You want to have an instrument that has long-term reliability. You don't want to have to visit the site every day and check up on your instruments. You want it to be real easy to use. Lots of people might use technicians in foreign countries to help manage their data and their site. And, the instruments themselves are light, easy to put up on the power. The low power demand is a really big aspect. A lot of places don't have electrical power to connect to, and just the overall practicality of the instruments. So now we look at the data itself. This is a Windows software, a couple screenshots here. You can see the CO2 H2O analyzer software and the methane analyzer software. This software is, you don't need any real programming. You just connect and have this data in front of you. You can see real-time values here. You can monitor quick diagnostics to make sure everything's working correctly. You can run your calibrations and validations, and you can pull up strip charts and graphs to view to make sure all your numbers look okay. Here's a picture of the LI-7550 Analyzer Interface Unit. This is a box that allows all the different heads to connect to, for example, the 7500 open path, the 7200 enclosed path, and the LI-7700 methane analyzer. All these instruments can come into the same box where all the data is integrated. You can also bring in sonic anemometer data, so you have your wind speeds, and you can have all these data sets together in one file. Some of the unique features of utilizing this box is you have a USB drive, which allows you to log your data. You have multiple Ethernet inputs and outputs, so you can connect to different instruments, different computers. It gives you remote access real easy. You have analog inputs and outputs. Again, that's for connecting sonic anemometers, for example. You can wire in a sonic anemometer straight into this instrument so that you can collect the wind data along with your CO2 and methane and water concentrations. And then we have the standard serial port, and also an SDM output is available for those that might have a Campbell data logger. Here's just an example of a screenshot from our 7200 CO2 analyzer Windows software. What you can see here, we're on the USB tab, so this is going to collect data on the USB drive. So the options you have, for example, is you can set your update rate here with just a click of a button in the drop-down menu. You can decide how often you want to split your files. For example, the typical people usually use the 30-minute splits. And on the right-hand side, you can see where you can just go through and click out the variables that you want to collect. And so it gives a lot of nice versatility. It's real easy to use. All you then do is click the Start button, and your data starts to collect.
Dave, this looks like a good place to stop for an audience question. I have a question about the USB drive. And it's how much data can be stored on the USB drives, and is there any issue with temperature?
If you look at a USB drive that comes with our system, we offer a 4 gigabyte industrial drive USB. And if you were to collect your data at 20 hertz, and you're collecting every single variable, I believe there's 52 of them. If you're collecting CO2, H2O, and methane, you have the whole suite of our instruments, that it's going to be a little under 7 megabytes an hour. So in most cases, to give you kind of a better example, is if you're collecting at 10 hertz, again, you're collecting carbon dioxide, water vapor, methane, and all the associated variables, all 52 of them, kind of a worst case scenario, that you're going to have about 4 megabytes an hour. That comes out to about 40 days. So your USB drive could hold about 40 days worth of data. Of course, if you reduce the number of variables that you want to collect, you can go much longer than that. In regards to issues with temperatures, the ratings for our industrial USB drive is can go anywhere from 85 degrees C down to negative 40 degrees C.
Thanks, Dave.
Okay, so getting back into the presentation here, we have a picture of a typical open path CO2, H2O, CH4 system. The three main components here are the instruments themselves, including the analyzers and the sonic anemometer. And we have a power system. In this picture you can see solar powers, which you don't see behind there is some racks of batteries. And we also have a tower to mount the instruments on. So to get a system like this up and running pretty easily, we've provided some technical notes to help with this. This particular technical note deals with solar power for powering Eddy Covariance flux stations. This tech note's on our website. It's pretty easy. It steps you through how to compute the total system wattage for your station. You can compute the number of panels and batteries that you would need. It helps you determine how many to use based on your latitudinal position on the globe. There's a worksheet and table to step you through all the calculations. There's some wiring diagrams and a list of suppliers to help. You know, this is really important, as a lot of Eddy Covariance sites don't have AC power. And so having instruments and a solar power system really helps you get those measurements made. We also have a tech note dedicated to the tower and mounting of the instruments. And so if you're looking for solutions on what's best for your site, for example, do you want to use a tripod or do you want to use a tower? We discuss the different new rail fittings, how to anchor the tower, suggestions for lightning protection, and also give a list of suppliers that might help in answering further questions for your site. Okay, so now I'm going to give the microphone back to Jayahung, and he's going to discuss the basic data processing principles. Thanks very much.
Thanks, Dave. Let me remind everyone that the next webinar in this series will be open for registration soon. Watch for an announcement online or in the webinar follow-up email. Jihong?
Thank you, Ashley. Thank you, Dave. Data processing is a very important part of the Eddy Covariance method. To get the final fluxes, we need more than just compute the fluxes based on the formula we discussed before. We need to take many other steps, as you see here. We don't have time to go over all the procedures. At this time, I will only explain the basic principles for coordinate rotation, frequency correction, and WPL correction. To keep the mean vertical wind speed equal to 0, we need to level the sonic at any moment perfectly. However, realistically, it's harder to do so. Coordinated rotation is a mathematical way to meet this assumption. In theory, we assume that wind speed and mixing ratio are measured simultaneously at one point, and all the eddies are measured. But in reality, sensors are separated, and they have measuring paths. Also, we use 10 Hz for data logging to reduce the loss of high-frequency eddies, and using 30 minutes averaging period to minimize the loss of low-frequency eddies. We still lose a very small amount of eddies. Frequency response correction is used to recover the lost eddies based on some well-developed mathematical models. By definition, mixing ratio is used in the eddy flux formula, but most gas analyzers measure density instead of a mixing ratio. Density is affected by the variation of temperature and humidity. For example, when temperature increases from stage 1 to stage 2, the mixing ratio of CO2 doesn't change, but the CO2 density decreases. WPL correction is applied to account for the difference between mixing ratio and density. Let's take another moment to see if we have received more questions.
Yeah, I do have a question from the audience. It is, we have heard of the opinions on sensor separation. What are your thoughts?
Yeah, I can take this one too, Jayahung. I know it's a good question, and I believe there's not a real clear answer here, but there's certainly things to think about. You want to have enough separation to avoid disturbance. Each sensor is not affecting the measurement of the other one. However, you still want to be close enough to be sampling the same parcel of air. And it's also important to note that this can be scientifically corrected, so it's not really an issue if you have them within the right distance of each other. And again, we're going to have that next webinar that goes into more detail about the installation of the instruments and how to set them up in the proper locations and distances.
Thanks, Dave. Before I turn the presentation back over, I'd actually like to pop up our third poll question.
It's very interesting to see what the people are using. Thank you for your participation. Eddy Flux data processing is conducted with computer software. To get accurate flux, the computer program must have all the required corrections. There are several pieces of software available right now, such as EddyRay, ECPack, and TK2. LI-COR is going to release a data processing software this month. It's named Eddy Pro. Eddy Pro does all the corrections for calculating the final fluxes. Eddy Pro has been tested against the commonly used data processing software. The results were consistent. As you know, it's impossible to cover all the details of the Eddy Covariance method with a webinar. For more information, please visit our website and download a free PDF copy or order a hard copy of this book. A brief practical guide to Eddy Covariance flux measurements. It provides more detail on the subject we discussed here. It also covers some area we haven't measured, such as how to validate your flux data with energy balance. I'm going to stop here to let you take part in our next poll and let Dave take over the talk. Thank you.
Okay, thanks, Jai Hung, and I can see the results from that poll, and it's always interesting to hear the various research and management applications that people are investigating. So I'm going to kind of step through some of these Eddy Covariance applications. The first one is probably the most common utilization for Eddy Covariance towers, and it's for ecological research. So, for example, if a researcher is asked to examine a particular ecosystem and answer a couple questions. For example, over the course of the year, is this ecosystem act as a sink or a source? So if there's more carbon getting absorbed into the ecosystem, it's acting as a sink for carbon. Now, if an ecosystem is releasing more CO2 than it's absorbing over the course of the year, then the ecosystem is a source. Some other questions might be, well, by how much? So you want to know the amount of carbon that is either being absorbed or released over the course of the year. And does it vary by year? Here's a quick graph of some typical data that you might see. So things that could affect the sink or source aspect of an ecosystem over the course of the year might be droughts, precipitation, different treatments, landscape changes. You'll want to also have continuous long-term data sets. Here you can see how the seasons affect the curves. You also want to notice how this is the same ecosystem over 2 different years. And you can see in one year, the ecosystem is a sink for carbon, and while the second year, the ecosystem is a source for carbon. Networks are set up to study these kinds of measurements all around the world using the Eddy Covariance method. This map here shows several different flux networks from Ameriflux, Asia Flux, China Flux, where towers are set up at different ecosystems so people can compare the measurements they see. People are interested in looking at light use efficiency, water use efficiency for plants. They might want to look how often crops should be irrigated, how much water should be used, or even how does fertilization affect the crop. There's also been a growing research into the area of biofuels. For example, how much water is necessary for growing the crops used for biofuels? Is there any kind of cost benefit in terms of carbon footprints for each of these? There's also a lot of people that are using Eddy Covariance for looking at wetland research. For example, on a particular wetland, how much methane is being released? How will hydrology affect wetland subsidence? Here's a site that was set up in the Everglades that's measuring both carbon dioxide and methane. You can see the results on the top graph. There's also people utilizing Eddy Covariance for land management applications. For example, with prescribed and controlled burning, how does that affect the carbon and water cycles of that particular ecosystem? A similar application in land management is we're looking at deforestation. You can see in the picture here where a large area of trees have been removed from the Amazon. Now, how does this affect the carbon and water budgets for this particular area? People are also using Eddy Covariance over the oceans. People studying ocean research, oceanography. There's boats, rigs, and platforms out in the sea that use the same technique to measure the carbon and water fluxes in and out of the ocean as well. There's a lot of discussion and debate about water rights. For example, how much water is needed for irrigation? You also might have endangered species. There's lots of discussion on how much that is needed, and one way to measure that is looking at evapotranspiration. Here's an application with research studying landfill or waste management. This is a method to measure how much methane could be leaking out of a particular landfill. We also have people interested in looking at urban studies. How are automobiles, buildings, people affecting CO2 and H2O cycles in a city setting? Here's an example of a green roof in New York. It's being researched by Wade McGillis. We also have applications in regards to carbon capture and sequestration, also known as CCS. In this application, you have power plants that are sinking CO2-rich gas back into the ground. What Eddy Covariance can be used as a detection method to try and find leaks back up at the surface. And finally, if you kind of look at a big picture, there's a lot of satellites that are being used to study the interactions between the Earth and the atmosphere. Eddy Covariance plays a large role in ground truthing these types of measurements. And, is Eddy Covariance something that can be used to even improve climate models? So I'd kind of like to ask one more poll here, our final poll. If we were to have an online community where people like yourselves could come in and discuss different applications or even Eddy Covariance research, is this something that would be of interest to you? So that kind of wraps up this particular webinar. I hope you found it informational. As I mentioned towards the beginning, we have a second webinar that kind of dives into the different instrumentation and the experimental design. We'll talk about the instruments that you would use, what kind of requirements you need, how to install the instruments on a tower, determine footprints, and what kind of maintenance schedule you should have for your instruments. You can also see the following 3 webinars after that will fall during the respective months that are listed there. So we've kind of put together all these additional resources as educational resources that we feel helpful not only to us but other researchers and scientists with understanding and conducting Eddy Covariance measurements. Of course, we'll be continuing this Eddy Covariance method webinar series. We have the guidebook for Eddy Covariance measurements put together by George Burba and Dan Anderson. and we'll have some dedicated web pages specifically for Eddy Covariance. We have the new user-friendly full data processing software that Jaya Hung spoke about coming up here in the next couple weeks. We also have a 3-day Eddy Covariance training course taught here at LI-COR. On our websites, you'll find places to register for that if you'd like to come in here, get taught by the scientists, and actually get your hands on the instruments, talk about all the implications and how to set up towers properly, and a day that's dedicated just to computing your fluxes, taking the raw data, stepping through software, doing quality assurance, quality checks on your data, and get you to the accurate computational flux measurements you're trying to acquire. Okay, looks like we have a time for a couple questions from the audience, so I'll go ahead and take those now.
All right, I have a few questions from the audience. The first is, can you explain a little more about the landfill application?
Okay, that particular setup was here at a landfill in Lincoln. And what's going on there is waste is buried, and you have anaerobic activity creating methane gas. At this particular landfill, there's vents that are located around the area that allow the methane gas to escape. And we went ahead and set up a Eddy Covariance tower to record the emissions of this methane gas. The concentrations and fluxes that we're seeing are really quite high. We see ranges of 30 to 40 micromoles per meter squared per second, or 2,300 milligrams per meter squared per hour. Recently, they've just started capping these vents to capture the methane gas and convert that to usable energy. And you'll probably see some posters and presentations put out by us and our scientists and research team later this summer.
Thanks, Dave. The next question I have is, you briefly discussed 3 corrections in the data processing. I thought there were more than that.
Yes, that's certainly true. It's also important to know the order in which you apply the corrections and assumptions. But there's certainly other corrections such as the unit conversions, despiking, detrending, time delays, and the frequency response correction actually contains a set of 8 sub-corrections. So those again will be covered in further detail in our in-depth webinar where we step through those. And also these are all explained in good detail with lots of references in the Eddy Covariance handbook.
Thanks, Dave. The last question I have is, you mentioned using a software program for processing data and computing fluxes. We have a data logger that computes fluxes on the fly. Can we use those? What is the difference?
Data logger programs can be quite different, so I can't answer that one for sure. But as just mentioned in the previous question, a lot of people utilize software to step through all the necessary assumptions and corrections. And software, like the one that we're going to be providing and the other ones we mentioned in the presentation, utilize all the corrections and assumptions and perform in the right order. And really, this is the best way to ensure that your flux numbers are accurate, and they can be used for publications.
Thanks, Dave. Before we close out of the webinar, I hope everyone's questions have been answered. Our panelists will stick around until they all have been, so please be patient. If you check the screen here, we actually have an Eddy Covariance measurement book, and it's available in electronic format if you'd like to download it from our website. But we also have this book for sale in hard copy on our e-commerce site, and you can see the website there that you can go and get this book from. And also, our next webinar will be available next month, so watch your email for a link to register for the next webinar in this series. Thank you for attending today's webinar. We hope the information was useful. When you're ready, please close out of this window and take a moment to fill out our post-event questionnaire. Your responses will help us to improve future webinars.